Good morning, everyone. My name is Boelo Schuur, and I am Scientific Vice President of the European Federation of Chemical Engineering, the EFCE. After being a board member of the Netherlands Process Technologists for 6 years and representing the Netherlands in the General Assembly of the EFCE, I have also served as the Secretary of the EFCE Working Party on Fluid Separations for 6 years. I've now been in the board of the EFCE since January of this year. I'm a chemical engineer by training, and I have received my degrees from the University of Groningen in the Netherlands. I built my career in academia, and since 2011, I'm in Twente. I climbed the ranks from assistant professor to full professor, and currently I hold the chair of Sustainable Separation Technology. I'm very happy to introduce this webinar on the role of thermodynamics in a changing world. Let me say a few things about the Spotlight Talk series. This is our 5th year, and we started in the 2020 with the COVID pandemic. But currently, we have no limitations on traveling anymore. But still, we see that this is a good concept, and we would like to extend this. In the even years, such as 2024, we have 2 sessions in the spring and in the fall. And in the odd years, where we have a European conference on chemical engineering, we only hold a spring series. Now, this year, this fall series, we had 13 of our working parties and sections involved in the organizations of short sessions of 3 or 4, or maybe even a few more talks on specific topics by leading industrial and academic experts. And this morning, we have a session about thermodynamics and transport phenomena. After this morning session, we still have another session tomorrow for which you can still subscribe. The complete program is available on the EFCE website. The EFCE promotes scientific collaboration and supports the work of more than 100,000 chemical engineers in 30 European countries and beyond Europe. And the EFCE's working parties and sections cover all major aspects of chemical engineering and are the core of our organization, forming the scientific engine that drives many of our activities. And they provide an important forum for technical exchange and networking among chemical engineers in Europe. I would like to thank all of the working parties and sections that have been involved in the past 2 weeks' activities, particularly today, the working party on thermodynamics and transport phenomena, and of course, Martina Poe from Toulouse, who organized all of these activities. So for now, I wish you a fruitful webinar, and I hope you enjoy. And I would like to give the word to the chair of the Working Party on Thermodynamics and Transport Phenomena, Maria-Grazia de Angelis.
Thanks a lot. Good morning, everyone, and welcome to this webinar. As usual in this series of Spotlight Talks, our Working Party on Thermodynamics is offering a session, and today's session is about the role of thermodynamics and of applied thermodynamics in particular in our changing world. So how we apply thermodynamics to topics such as sustainability, energy transition, and circularity. And let me tell you that thermodynamics is at the very core of this revolution. So first, I will start by saying a few words about our working party. It is a very active one, and if you want to be a member of our working party, you can follow our activities on our website, on our LinkedIn group, and you can contact me or the vice chairs. I am a professor of thermodynamics and materials and processes at University of Edinburgh, UK, but previously I worked in University of Bologna in Italy. And now I am leading this network of people interested in computational and experimental thermodynamics. We are a network of experts, both from academia and industry. We are a mixture of young and more experienced people and professionals. We all have a passion for thermodynamics, and we would like to take away the fear of thermodynamics, especially from students. So we care a lot about educational aspects of thermodynamics, we publish position papers. One was published 2 years ago in industrial and engineering chemistry research, and another one is coming up about the role of thermodynamics in pharmaceutical applications. We distribute awards to young academics, but also to more experienced ones. We organize conferences and events such as the workshop on the industrial use of thermodynamics. And we do a lot of networking, not only inside Europe, but also outside Europe. So even if you are not a European professional, you can still join our network and attend our events. We provide guidelines and best practices, for instance, for regarding the collection of data and the publication of high quality data in research journals. I also have been told to remind you that during these talks, you are not allowed to ask. Of course, you are encouraged to ask questions, but you are not allowed to ask them directly. You have to use the Q&A chat function of this webinar. So today I'm going to chair and moderate this webinar together with Dr. Christoph Held and Dr. Antoon from Germany and Netherlands, respectively. And we have 3 very interesting talks by experts in the fields of modeling of carbon capture, energy and exergy, and thermodynamics for refrigerants.
Then I'm very happy that we have today Raphaelle Thery. She's an associate professor in Toulouse, and she will tell us something about exergy and applications to process optimization. Raphaelle, screen is yours.
Yeah. So that's the good one. Yes, a bit. Yes. Is it okay?
Perfect.
Screen? Yes, perfect. Thank you very much. So thank you very much for your introduction. So I am an associate professor in Toulouse INP-ENSIACET and in the Laboratoire de Génie Chimique in Toulouse. And my research topic essentially concerns development of PACE, process system engineering methodology dedicated to the optimization of energy efficiency of industrial sites. So actually, Europe aims to be the first carbon neutral continent, and the development of efficient strategies to encourage decarbonization of the industrial sector is relevant because this sector accounts for almost 40% of emissions. Among the different strategies existing to reach this goal, the process retrofit, dedicated to the improvement of energy efficiency of industrial processes, appears as one of the most crucial ones. So in chemical engineering, pinch analysis and exergy analysis are key methods for improving industrial energy efficiency. So pinch analysis focuses on maximizing thermal energy recovery within processes, often leading to the development of efficient heat exchanger networks. The problem is that only considers thermal energy. Exergy analysis, on the other hand, includes thermal, mechanical, and chemical exergy energy components. It allows them to assess inefficiencies from irreversibilities, but also from environmental losses. However, exergy analysis is complex. It lacks systematic methodologies and computer tools dedicated to the proposal of practical retrofit solutions. And it still heavily relies on engineers' expertise. So in the end, it appears that these two approaches are highly complementary and would benefit from being combined. Relying on this idea, the COOPER approach was developed through a research project funded by the French National Research Agency and involved partners such as the Veolia and Prosim company and the Laboratoire de Génie Chimique and AgroParisTech. And the project goal was to create a new methods that combine optimization pinch analysis and exergy analysis to retrofit industrial processes for improved energy efficiency. The methodology was then implemented in the ProSimplus simulation software. So Douglas suggests that you can think a process like an onion with layers. When you're designing a new process, you work through these layers, starting from the core and moving outward. But if you're analyzing an existing process, it's usually the opposite. You start from the outer layer, like utilities and heat exchanger network, and try to keep the core intact as much as possible, only digging deeper if you really want to. This idea is what the co-pair approach intends to implement. So, first of all, the co-pair approach begins with data collection, statistical analysis, and process modeling. Reliable and accurate data for the operational process are essential for effective modeling. The second stage will focus only on the two outer layers of the onion. The approach is essentially based on pinch analysis for the retrofit of heat exchanger network and utility system. I will not go into detail of this aspect as it's not the fundamental subject of our presentation. If the engineer feels that the savings from the first steps aren't enough, then there's a third stage to go deeper in the process. In this stage, pinch analysis is combined with exergy analysis to get more insights. So I will explain how the combinations between pinch and exergy will work and show some example later in the presentation. Let's take an example, an academic example of an ammonia production process to illustrate the methodology. A functional analysis of this process has permitted to identify the several functional areas. These areas are modeled and mixed together in the ProSimplus software. As we will see later, the exhaustive modeling of the process plus utilities are really necessary to perform a relevant exergy analysis. Given this model, the first step aims at performing an exergy diagnosis and then to formulate some improvement suggestion based upon this analysis. So let's go to the exergy concept. Exergy originates from the early 19th century with the Carnot engine and the concept of energy quality. The term derived from Greek, ex meaning external and ergos meaning work, was first used in the mid-20th century and is also known as available energy. Basically, exergy represents the maximum useful work of a system can produce as it reaches equilibrium with its environment through reversible processes. So it's quite complex, but we are used to saying that while enthalpy measures energy quantity, exergy will indicate some information concerning energy quality. Using exergy balances helps engineers choose processes that minimize wasted or destroyed available work. First, exergy was mostly seen as a complex concept suited for thermodynamic experts. Our role was to make it easier to use in order to disseminate this concept in the engineer world. So we decided to integrate it into a simulation software like ProSimplus, making it possible for engineers to perform exergy balances just as easily as for traditional enthalpy balances. As illustrated in this Sankey diagram, enthalpy is conservative. It is neither created nor destroyed, but converted from one form to another, mechanical, thermal, and chemical. In turn, an exergy balance is depicted using a Grassmann diagram. In non-ideal process, exergy can be either wasted, meaning it is released to the environment without being recovered here, such as waste heat, for example. It can also be destroyed here, and due to irreversibilities in the real processes. These irreversibilities arise from factors like non-isothermal mixing, non-isobaric mixers, thermal losses, pressure drops in the unit operation. And we must also say that some irreversibilities, such as heat transfer with non-null temperature difference in heat exchangers, and chemical reaction, chemical conversion in chemical reactors, are unavoidable because they are essential to make the process economically viable. In this equation, we can find the different terms. The first term we can find is the BW here, which is the exergy of mechanical work. So the mechanical exergy is one of the most qualitative form of energy. So here BW is equal to W. Excluding the irreversibility terms, which is there, you know, which is deduced from the other ones, we can find also some exergy of material streams here. We make the difference with the used material stream, which is there, and the waste material stream, which is unrecovered. Assuming that kinetic and potential contribution to exergy remain constant in chemical processes, the remaining contributions that must be evaluated in the simulators are physical and chemical ones. So to evaluate this term, a general formulation for the exergy had to be implemented in ProSimplus. The formulation to be implemented in a generic software must need to be applicable across different thermodynamic models and also valid for liquid vapor streams. As you can see on this diagram, we can compose the exergy composed of different contribution, 3 contributions. The first one is the thermal contribution of exergy, which is a minimal work for the streams to go from the process states, that is to say the process temperature to the environmental temperature. The mechanical exergy, which is just the minimal work required to go from the process pressure to the environmental pressure. And finally, the chemical exergy, which is related to the minimal work required to go from the process composition to an equilibrium mixture made up of environmental components. This is the so-called chemical dead state. So this calculation has been implemented. As you can see on this diagram, we have no heat stream appears in this diagram. Why? Because as illustrated here, these old and cold utility streams must be represented as material flows in the modeling simulation, As a consequence, a relevant exergy optimization of the process under study necessarily requires to build a complete model, including the core process, but also the utilities. So, what's the goal of exergy balances? Basically, it helps us pinpoint which part of the process should be improved in priority. To get a meaningful exergy map for the process, it is useful to look at KPIs such as exergy efficiency. Within the exergy module implemented in ProSimplus, we can set up an exergy balance and establish a very efficient formulation of exergy efficiency. So let me explain this formulation. In any unit operation or process zone, a large part of exergy passes through the system without being modified. For example, in a heat exchanger, the heat exchanger will only affect the thermal part of the exergy, which is there. Okay, but the chemical and mechanical part of exergy will not be modified. So in a heat exchanger, the transiting exergy will be composed of the mechanical and chemical contributions. Okay. By adjusting the exergy balances, deducing the transiting exergy on both sides of the equation, we can define 2 key concepts: the consumed exergy and the produced exergy. And this approach helps us create a much more efficient formulation of exergy, of efficiency, which will be implemented in the ProSimpli simulation. Unlike other formulations, such as, if you know, rational efficiencies, intrinsic efficiency works really well for systematic evaluation in a simulator. Another interesting point is that when we divide each part of the exergy balance by the consumed exergy, we can connect the three coefficients, the three KPIs coefficients that helps us analyze the system. Here you can find, you can show that the sum of intrinsic efficiency, intrinsic losses, and intrinsic irreversibilities adds up to 1, so that we can use a ternary diagram to plot each area in the process visually. The more the point is at the top of this diagram, the more the more efficient the zone is. An inefficient point located on the right side of the diagram indicates a need for better recovery of exergy waste, of waste stream recovery. Whereas a point located on the left side of the diagram indicates a section that suffers from irreversibilities. And finally, the size of the point is proportional to the amount of destroyed or wasted exergy. So coming back to our illustrative example, you can find all the points concerning the different section of the process here. So here you have the colors, and here the different point of all the section of the process. For example, it seems obvious that the mixing and compression section there need to be improved toward the reduction of irreversibilities, whereas here the separation and the purge section will be improved in terms of recovery of external wastes. So let's begin studying the mixing and compression section. This diagram illustrates the intrinsic irreversibility and the relative irreversibility of each unit operation of the section. As you can see, the mixer contributes to more than half of the irreversibility of the sections, and the total intrinsic efficiency is almost equal to 100%. So this irreversibility is mainly due to the non-isothermal mixing in the mixer. The remaining irreversibility here is due to a high pressure drop in the compressor. Let's look at a few changes that we could introduce in the structure to reduce the irreversibilities. First off, we could imagine to add heat exchanger to each inlet of the mixers. This would help achieve an isothermal mixing and then reduce exergy losses there. For the compression section, we could imagine to add an extra stage of the compression with a heat exchanger between the two stages. One we must to keep in mind there is that at this stage of the methods, we do not include any heat integration, and we model only the hot and cold requirements necessary to perform these structures. So in terms of optimization variables, the optimization variables, unknown variables that must to be optimized, but these are here the temperature and pressure in the compression stage, the outlet temperature in the mixer. We have also constraint variables, and we have also variables which will be deduced from simulation through mass and enthalpy balances. Here you can find the superstructure implemented in ProSim+. As you can see, two new modules introduced in the simulators are switch modules, which enables to implement a decision that will be made by the optimizer to choose the one-stage compressor or the two-stage compressor. Let's consider now the separation section here, which should improve the output stream recovery. According to ProSimplus exergy losses, according to ProSimplus, we can find that the exergy losses are mainly due to chemical exergy, as you know. If we go on the composition of this here, if you go to the composition of the pH here, you know that it's mainly composed of hydrogen, methane, and ammonia. So we could imagine to implement complex costly separation sequences, but at this stage, we will better imagine to solve the mechanical and thermodynamic and thermal exergy loss. Most of the loss are mechanical exergy, and to a lesser extent, the thermal exergy here. So then we could imagine structures which will implement a thermomechanical recovery by introducing heat exchangers with output temperature variable and turbines with the output pressure variable. So again, this structure does not include any heat integration. The modeling only displays the hot and cold requirement at this stage. Here again, you can find the switch modules that we help to decide between the thermomechanical recovery or any or no mechanical recovery. Given these superstructures, the next steps will consist in performing a multi-criteria optimization in order to decide which structure should be the best. Sorry. So we must know that the exergetic analysis is the most powerful tool to propose and to help pinpoint the inefficiencies to construct the superstructures. However, we must say that to be adopted by engineers, the approach should, in the end, propose processes that combines energy efficiency and economic viability. And coming back to the mixer example, which is a very good example, if we had two upstream heat exchanger in the mixer, then we will reduce the reversibility to 0. It's okay, but this comes with a trade-off because it will increase the hot and cold utility requirements. So we should add extra heat exchanger only if they lead to the definition of integrable hot and cold stream that will contribute to a better internal heat recovery. So this is where we see the value of combining pinch and exergy analysis, because exergy analysis will act as a diagnosis tool to identify areas for improvement or to construct to define the structural modification, while pinch analysis will provide a concrete evaluation criterion to fine-tune the operating parameters of the process. So here, among all the criteria we can imagine to the optimization, we could find, for example, as illustrated before, all the minimal energy requirement or maximum recoverable energy calculated with pinch analysis and using the pinch modules, which is available in ProSimplus. We could also imagine to reduce the net mechanical work consumption. And we could also imagine to optimize the CapEx using the cost module, which is also available in ProSimplus. For this purpose, the fifth ProSim software can be combined with a Midako module for multi-criteria optimization. It is based on a hand colony meta-heuristic approach. So as you can see here, you have different windows that enable to construct the optimization model in ProSim by defining the variables, the objective function, and so on. So if we run, in this one, we have defined 3 optimization criteria. energy consumption, minimum cold utilities, and minimum hot utilities. And we obtain a Pareto front, which allow to obtain different solutions that will minimize each of these criteria. So just to finish in this presentation, I will just illustrate the result obtained for the scenario, which guarantees a compromise between all these criteria. So here you have the result of the superstructures, and you find in green the new unit operation that should be introduced. You can notice a gas turbine layout at the output of the reactor, thermomechanical recovery, two-stage compressors. As you can see on the result, you see that between the comparison between the nominal process and the optimized process, you find that there is a significant improvement of the recoverable energy here, you know. So we must know that here in this sequence, we have no integrated solution, but just requirement. So the last step must be the definition of the heat exchanger network. So for that, we use a reflex software that we developed in the Laboratoire de Génie Chimique, and we will try to put on this structure the heat exchanger network. And finally, we obtain this kind of integrated process with 4 integration heat exchanger in green here, you know. And when we look at the results, we see that we have a significant improvement of performances concerning the cold utility consumption, the mechanical work consumption. You can also produce much more steam recovery in this heat exchanger, more than twice. And it's really interesting. And also you can see that the exergy efficiency is better than in the former one. So to conclude, we developed a new approach focused on retrofitting industrial sites by smartly combining pinch analysis with exergy analysis. Traditionally, this method was used for retrofit existing processes, but actually it is also used for the optimization and the conception, grassroots design of process dedicated to the production of e-fuels. And the problem is that we must admit that the construction of the superstructure here only relies heavily on the engineer expertise. And to fill this gap, we're currently working with one of my PhD students on the development of a new framework dedicated to the automatic construction of the superstructure here, using ontology paired with rule-based reasoning. Additionally, we intend to perform advanced exergy analysis in order to make the difference between avoidable and unavoidable exergy losses. So, of course, we keep also on working with FIF-ProSim in order to contribute to the energy modules development, actually. So here are the contributors of all these works. I would like to thank, and I'm ready for some of your questions, if you want.
Thank you, Raphaelle, for your excellent presentation. It shows a very nice way to introduce exergy analysis to really analyze how sustainable your processes are. Of course, it remains a challenge, I think, because exergy indeed is a difficult topic to grasp. The floor is open for questions. As said before by Christoph and Grazia, you can put in your questions in Q&A. So we are looking forward to that. In the meantime, I have some questions for you, Raphaelle. And on slide 30, you introduce an additional heat exchanger in your compressor system to get closer to reversibility, I guess, so better exergy usage. But it also means 2 compressors, and typically that there's a huge penalty. in terms of costs. Could you comment on that?
You're really right. And unfortunately, for the moment, I did not implement the introduction of CapEx in criteria in the optimization. To be honest, it's actually it's currently on development with one of my PhD students, because we found some implementation problems that are currently solved with one of my PhD students. But you're right, you should introduce in one of the Pareto front a criteria concerning the cost. It's obvious if you want to obtain viable solutions. Yes.
Yeah. Okay, thank you. You also mentioned had that this superstructure approach. In one of the last slides, you imagined that you're thinking about artificial intelligence solutions. Are you thinking in terms of the work by Arthur Schweizman in Delft, who's generating P&IDs automatically, or what are your thoughts?
Sorry, because I have a noise on my computer, so I did not answer the last part of your question. Do you think?
The question is how the artificial intelligence part. How do you think about that?
Yes.
Is that work?
Yes, one of my PhD students actually currently work on this part, because it's actually the gap and the last thing that we must develop, and using artificial intelligence. For the moment, we intend to use work that has been developed for the process synthesis, design synthesis, and to adapt these methods for the retrofit of industrial process based upon our exergy diagnosis. So it's a coupling between ontologies that aims at modeling processes from a generic point of view, and rule-based reasoning. So artificial intelligence, for the moment, we imagine it to implement it using traditional and very classical rule-based reasoning, in order to implement in a database all the really interesting and classical way to reduce irreversibilities. And at the end, maybe we could use, and we used also some other things, such as the case-based reasoning. For example, at the so I did not share. I don't share my student. Yes, no. So, for example, at the in the cooling section of the process, we imagine to use and to implement. So, I just come back to the process to the process. Where is it? Here. Okay. If you can see here in the integrated process.
Sorry, Raphaelle, you're not sharing your screen at the moment.
Oh, well. Okay, you're right. Yes. And here?
Yes.
Okay. So on the integrated process, you can find that we have implemented a gas turbine layout. And this gas turbine layout has been inspired much more by case-based reasoning, because we have seen in another publication that for output pressure, which is made up of high pressure stream and high temperature streams, we could imagine to recover much more the pressure part of the stream. That's the exergy part of the thermal part of the streams, by introducing a layout. And this has been inspired by other publications that choose to implement this kind of layout for another process. And the idea was to adapt existing layout for another processes to our processes, using a case-based reasoning, much more than rule-based reasoning. So the idea was to couple and to combine rule-based and case-based reasoning. So in the process and the construction of the superstructure.
Okay, thank you for your very elaborate answer. Also, in view of time, I would like to thank you again for your very nice presentation. And would like to move on to our third and last speaker of today. So I'm very happy to introduce Professor Fèlix Llovell of University at Universitat Rovira, Virgili. He has a very strong background in computational thermodynamics, did his PhD at the Spanish National Research Council, and then moved through the ranks and stayed at different places in Delft, in the Netherlands, in Conception, in Chile, at the Imperial College, UK, and became an assistant professor in 2021. His work is highly recognized, as is seen by his selection amongst the 25 best world emerging investigators in chemical thermodynamics by the Journal of Chemical and Engineering Data. And he is recipient of the Young Researcher Award at the prestigious PPD conference. Today, he will tell us about the role of applied thermodynamics in the area of refrigerants. Looking forward to your presentation.
Okay, thank you. Thank you very much. It's a pleasure to have this opportunity. So I'm going to share my computer, my presentation. Okay. Okay. Well, as said, thank you very much for the very kind introduction. I would like to take the opportunity to talk a little bit about part of the research that we have been doing and how applied thermodynamics can help in a very interesting area such as the one of refrigeration. Okay. So as I was introduced, I come from Universitat Rovira Virgili, which is located in Tarragona in South Barcelona in the area of Catalonia in Spain. And the chemical engineering department has a strong connection with the Tarragona chemical cluster because we have currently one of the largest chemical hubs in Europe, indeed the largest one in Southern Europe. So basically, there is a lot of interest in developing sustainable processes to make our chemical processes affordable. And I think I don't need to convince you about this, but I will just quickly move on to that about the scientific evidences on the planet's average surface temperature increasing and going into an exponential rise, particularly in the last 25 years. And the consequences of that, we have been, unfortunately, suffering some of them. And here I would just like to highlight a couple of images from the tragedy that has occurred in Valencia due to the very severe storms that have caused floodings and more than 200 people dying. Of course, there is a lot behind this, but the point is that there are more and more evidences that move into the same direction. We need to take action onto climate policy. And although CO2 is always seen as the main guilty of this film, there are other greenhouse gases that have an important action. One of them is hydrofluorocarbons. Hydrofluorocarbons are synthetic greenhouse gases that are commonly used in refrigeration processes, and although they are classified within the F-gas section and account only for 3% of the total emissions, the global warming potential effect is up to 10,000 times greater than CO2, depending on the gas that is used. And its atmospheric lifetime is up to 50,000 years. According to many statistics and works that have been done, they can be responsible up to 45% of climate change by 2050 if no action is taken, which means a 0.5 Kelvin increase due to the action of these gases. Of course, there has been in the last years the development of many CO2 equivalent emission avoidance strategies, and those also include the restriction and decrease of the use of hydrofluorocarbons, particularly in refrigeration processes and also in the use of organic Rankine cycles. We have already a previous successful story concerning the Montreal Protocol, which was the phase out of chlorofluorocarbons in order to avoid the hole in the ozone depletion potential. Okay, at that point, it was relatively easy to move from chlorofluorocarbons to hydrofluorocarbons because there was not a loss in efficiency in the processes. But now the increase in the CO2 equivalent emissions is causing the global warming has provoked the Kigali Amendment, which basically aims to phase down hydrofluorocarbons by 80% by 2047. Okay, so basically this is an agreement that has an amendment that has been ratified by almost all countries in the world and poses several challenges, particularly for the refrigeration industry. Indeed, the European directives are even stricter in some cases, imposing a regulation in mobile air conditioning systems, establishing limits of global warming potential above 150. And the last recent update implies also an overall management of F gases and a steeper quota in terms of restrictions. The American AIM Act in the United States has also directed a phase down production of consumption of hydrofluorocarbons. Basically, what I am trying to highlight here is that there are several rules that complete the Paris Agreement and the already maybe a little bit old Kyoto Protocol in order to reduce greenhouse gas emissions. As I said, the population covered by the Kigali Amendment reaches 85% almost, and it is important to consider that it is very necessary to reach this agreement in order to decrease the emissions up to something that can be reachable and achievable for the world. There has been a big evolution in refrigerants since the very beginning. In the beginning, when refrigeration was born after the Industrial Revolution, whatever work was used, this was the first generation of refrigerants, and toxic and flammable compounds were used. After some time in the decade of the 30s, safety and durability was looked for, and chlorofluorocarbons and hydrochlorofluorocarbons were born. They were very good refrigerants that work efficiently in a secure way. But with some time, it was discovered that they were also causing an impact on the ozone depletion potential. That's why, in order to protect the ozone layer, non-ODP refrigerants appeared, and hydrofluorocarbons became the leaders until now, where we have to look for new solutions. These new solutions go through the use of low global warming potential systems, including hydrofluoroolefins, the same CO2 that was at some time forgotten, and also the use of hydrocarbons, always looking for a combination that is safe enough, considering aspects such as technical performance, safety, and flammability. So the fundamental aim of the work I would like to present is to show how thermodynamics can help in this process, how help to rationally design fourth generation drop-in to be used in air conditioning applications. For this purpose, we want to go from the molecular-based models, from basic thermodynamics, to analyze the thermodynamic behavior of the compatibility of lubricant oils in refrigerants, check how these models can be used to study and understand low global warming potential refrigerants that can be used as alternatives, optimize the air conditioning cycles using these tools and other computational techniques, analyze what is the environmental impact of these new mixtures, estimating the carbon footprint, simulate these drop-in replacements to assess the fourth generation compatibility in order to minimize retrofitting cost, and finally implement the 4E, which means energy, exergy, environmental and economic analysis to assess cooling technologies, meeting the United Nations Sustainable Development Goals. So basically, the tool that is used here is the soft-shaft equation of state, which is a variant of the classical shaft This is a molecular-based equation of a state that uses the Helmholtz energy to estimate the total energy of the system as a sum of contributions coming from a series of physical effects. Indeed, the equation, as I said, comes from the contribution of Chapman and Gavins, and this is the variant developed by Felipe Blas and Lourdes Vega. And as many other soft equations, it splits the energy, the Helmholtz energy, in several contributions. We have an ideal contribution. We have a reference term that uses a Lennard-Jones intermolecular potential. We have a chain term that includes the contribution due to the covalent bond that is formed between the different monomers forming chains. And in that particular case, there is another term which is the hydrogen bonding term, the association, that is not included here in this case because we are not going to use here in that contribution, because we explicitly are going to consider a specific term for polarity, which is one of the most important contributions in refrigerants. Okay, so basically the famous association term of SAFT is not included here in the molecules that we are going to study. As I said, a refrigerant, a hydrofluorocarbon, or a hydrofluoroolefin will be described as a sum of monomers that have a particular dipole moment. In that case, we have three molecular parameters that are called the chain length, the segment diameter, and the dispersive energy between the segments that characterize these monomers that describe our molecule. Apart from that, we have two additional parameters coming from the polarity of the moment, the dipole or quadrupole moment that is fixed according to the available experimental data at vacuum conditions, and the fraction of polar segments that is integrated according to an approximate calculation where we see how much of the molecule is affected by the polarity. In that case, there is a classical optimization using the saturated liquid density data and vapor pressure in order to describe the vapor-liquid equilibria of the system. As I said, at the end, we end up with a total of 5 parameters. I would say 4 because this one, the dipole moment, is taken from experimental data, and also the fraction of polar moments is kept within a reasonable range. When we deal with mixtures and multi-component systems, we need to correct deviations due to the asymmetry of the compounds with different size and energetic interactions. There are 2 binary parameters, one of them related to the size and one of them related to the energy. In this work, only the energy one will be used, with the exception of some particular mixtures with lubricants. But in most cases, there will be only one of them. This parameter is used using the classical Lorentz-Berthelot combining rules. And finally, the van der Waals one-fluid theory is used to calculate the Lennard-Jones term. Okay, so first of all, the first part, in order to understand how we are going to apply this into an air conditioning system, is to have a very correct and accurate characterization of refrigerants. For this purpose, a total of 18 common refrigerants, considering 3rd generation hydrofluorocarbons and 4th generation hydrofluoroolefins, are used in this work and characterized. As I said, the information is done in the manner I explained before. The dipole moment is specified experimentally, and the fraction is estimated considering the amount of fluorinated atoms that there are in the system and how they affect the polarity. These calculations can be done using different programs that estimate the charge distribution, such as, for instance, Cosmo RS or Avogadro. Once this is done, the rest of parameters are fitted, and these are some examples of the vapor-liquid equilibria of these different refrigerants. As you can see, this is the temperature density diagram and the pressure temperature diagram. We can see that there is an excellent agreement in all cases. And one manner to validate this information is to check other properties that have not been used in the fitting. Here we can see how, for instance, the enthalpy of vaporization of these compounds, the density at one phase, or the speed of sound are predicted accurately. This step is very important in order to ensure that not only the properties that have been used in the fitting are good, but also these other properties. And in this case, we will see that there are 2 properties that are particularly important. The enthalpy and the entropy, because these properties are crucial in order to study our air conditioning cycle. The enthalpy and the entropy are also predicted and compared to experimental data. I didn't say that, but lines are always the model and symbols are the data. And we can see that there is a very good description in all cases. That allows us to develop the pressure enthalpy and temperature entropy diagram of all fluids, also including mixtures, such as, for instance, the Air 410A, which is a mixture between two different hydrofluorocarbons. Once we are confident, we deal with the different mixtures, and here we study not only mixtures between hydrofluorocarbons, but also hydrofluorocarbons and alkanes and other possible compounds that can be included in as alternatives. Here we can see that all these mixtures are predictions. When we have a 1 here, it means that there is no fitting here, no binary parameters. And we can see that also several CO2-based binary mixtures can also be predicted in very good agreement. Concerning the characterization of fluorinated compounds between hydrofluorocarbons and hydrofluoroolefins, or hydrofluorocarbons and hydrofluorocarbons, we can see we have studied at least 50, 60, 70 different binary mixtures, and in all cases, it is possible to describe the vapor-liquid equilibria either using a prediction, which means Chi equal to 1, or using a value which is very, very close to 1. In all cases, we can see that the description of the system is very, very accurate, and in only very, very few cases, we have a binary parameter that deviates from the predicted value. All this stuff is done in order to be sure that the results I will show now are accurate, okay? So I would like to highlight two cases. The first one is the lubricant compatibility on refrigerants. The lubricant characterization is a very crucial aspect on refrigerants because although this is not desirable, there is always leaks. There are always leaks in the compressor, and there is always contamination of the refrigerant due to the presence of oils, okay? So it is very important to understand when this is going to affect too much to the performance of the system in order to know when it is necessary to change and clean the system, okay? So in that case, we are using thermodynamics. We are studying two families of esters, pentaethyl esters and polyethylene glycol dimethyl ethers, two types of lubricants that are very common. We are studying them, and we are studying their performance into a very classical and interesting refrigerant, which is Air 513A, okay, which is a mixture of a hydrofluorocarbon and a hydrofluoroolefin. So in that case, we characterize first of all the lubricants as they can be seen here. These are pressure, temperature, and temperature density diagram. We can see that we can use a very simple model with only 3 parameters that are fitted to this data and that follow a pattern, a trend with the molecular weight. So the M, the sigma, and the epsilon can be correlated with the molecular weight using linear relations. So we can predict any member of this family, even though there is no data. Same is done for the family of polyethylene glycol dimethyl ethers. Using this information, we can develop a correlation to estimate these parameters. So this is an easy manner to have a description of these lubricants. Once this is done, we check the solubility of refrigerants in this lubricant, or the lubricants in the refrigerants, okay? Using the soft equation of state, we use available experimental data in order to describe our model, okay, and fit this. And once we have done that, we predict the behavior at different conditions in order to check. What are we interested? We are interested in maximizing the solubility and avoiding the immiscibility. So for instance, it would not be good to have PEC 7 here, because here we can detect an immiscibility. Remember that a leak will have a very small amount of oil and a big amount of refrigerant. So we will be in that area, okay? In order to check this, we have calculated the Henry constants of the two gases, the two refrigerants involved in the mixture 513A with a series of lubricants, and have looked for the lowest value that accounts for maximum solubility, avoid immiscibility, and also a qualitative criteria related to the viscosity. So finally, after doing this study, which found that PEG5 was the optimal choice, and then once we have the optimal choice, we check the impact of this in case of leak. Here we are doing a comparative study where we are checking the COP, which is the performance of the system, the coefficient of performance, and here we are putting 3 scenarios. The first, this is done with PEG5 and a comparative study with 3-ethylene glycol dimethyl. In this comparative study, we check the possibility of having a 1% of mass of the oil, which means we have a leak, but still the system should work. And here we can see how the coefficient of performance has almost no decrease with PEG5, but has experienced a 1% decrease with 3-ethylene glycol dimethyl. If we have a 3%, we can see that the decrease in the second case is up to 3.5%. And in the case of 5%, which should be avoided, we have a decrease of 5% in this case and 1.5 in the upper case. So basically, this is an easy tool, a very easy tool that can tell us when it is necessary to change and to include a separator module to purify the refrigerant in a predictive manner. We can choose the refrigerant that we want, and we can choose the lubricant, and doing this type of studies, it is possible to make this type of predictions that are very useful for industrial purposes. The second contribution I would like to show is the drop-in assessment of sustainable refrigerants. Okay, so basically, what does it mean? What we are intending to do is we are intending to study a simple vapor compression refrigeration cycle that is well known. Here you have the 4 stages. I will not go into the details. You know that we have a system that goes through an evaporation, then we have the compressor, the condenser, and the valve. So this is a classical cycle for refrigeration. And what we are interested in this case, these are the pressure entropy and the temperature entropy diagrams. Remember that all this information are obtained with the previous equation that I highlighted. What is this is the procedure to do the calculations of the cycle. Okay, I will not go now into the details, but these calculations of the enthalpy and entropy at each stage can be done using the previous equation. And what is the purpose? The purpose is to move from the 3rd generation of refrigerants towards a new 4th generation of refrigerants. Here we can see that there are already some transitional refrigerants, but what we intend to do is to go from these global warming potentials that are very high to a global warming potentials that can reach the standard of 150, according to the European Union rules. And to do that, what we are going to do is we are going to check several criteria, most of them based on thermodynamics, in order to find a proper solution. There is a second stage, okay, including LCA analysis and advanced cycles that will not be explained in this presentation. So basically, the first thing that we do is we do a bunch of studies concerning more than a total of 342 binary systems that are split in combinations with the refrigerants that you have seen previously in terms of in ranges of composition of 0.1. And we check which ones have a global warming potential below 150. From this, only 75 account for this criteria. The second technical criteria is the glide temperature. The glide temperature is the difference between the bubble and the dew points, and it must be as low as possible in order to the mixture to behave as a single refrigerant, as a pure fluid. According to this, these calculations can be done at different conditions of pressure and temperature, according once again to the conditions of the evaporator and condenser, and imposing a criteria of 0.1, only 2 mixtures reach this condition. So the next step is the safety criteria. The safety criteria involves the calculation of the flammability. This is, in this case, this is not done using any thermodynamic equation. This is done using the Linteris equation, okay, which takes into account the adiabatic flame temperature and the amount of fluorine atoms present in the system and establishes a normalized flammability index. We accept any of the mixtures that have are classified as A1 or an A12 according to their SRI, and we end up with a total of 8 possible candidates. These candidates are expected to substitute R134A and R410A, okay, which are the 2 most common commercial refrigerants used nowadays. The next step involves the thermodynamic analysis, and the thermodynamic analysis is done first of all analyzing 3 key performance indicators: the volumetric cooling capacity, the discharge line temperature, and the condenser pressure. Particularly the volumetric cooling capacity is very important, because if we need to substitute these ones, R134A and 410A, we need a similar volumetric cooling capacity. So what we do is we study the volumetric cooling capacity using the thermodynamic information, and we check which mixtures are similar to R134A and 410A. What we can see for 134A is that mixture number 2, 3, 4, and also 5, 6, 7, and 8 have a very similar volumetric cooling capacity. 1 is out of the scope. For the case of 410A, 1 is the closest one, although it is clear that there is not a simple and easy solution. This study is done for all drop-in key performance parameters, and finally we end up with 4 that have a good compatibility, okay, which are mixtures 2, 3, 4, and 5 that are indicated here, okay. 3, 6, 7, and 8 that are good, but a little bit less good, and blend 1 that is not good to substitute R134A because it has a low compatibility. For the case of R410A, the only possibility would be blend number 1, but still using partial retrofitting. Some modifications should be done in the compressor. Once we have some potential candidates, particularly for 134A, the next step is to check the technical performance. Here we check different important parameters. The most important one is the coefficient of performance and the exergetic efficiency, but other aspects are also considered, and they are plotted in a spider diagram. We have seen a spider diagram also in a presentation before. And here what we can see is that in terms of the coefficient and performance and exergetic efficiency, mixture number 5 has a relatively good performance. This is the mixture between 2 hydrofluoroolefins, okay? This again allows us to decide which one is the better according to the criteria that we want to fix and the weight that we want to give to the different characteristics. The same study is done for R32 and 1 and blend 1 for the substitution of 410A. Here what we can see is that the already existing R32 refrigerant is very good and it performs better than our blend, our alternative blend. To complete the study, an environmental analysis is done considering direct and indirect emissions. Indirect emissions are very important because they are related to the country-dependent energy mix, okay? So basically, to make long story short, once we know that our blends have a lower global warming potential, we also need to check what is the impact of their use in the compressor and how this electricity is produced, okay? So basically, the conclusion that we reach here is that indirect emissions may be more important than direct emissions. So it is also very, very important to consider how the energy sources are taken because they have a strong impact regardless of the refrigerant fluid that is used. Finally, the techno-economic analysis is also done, and the results highlight that using blend 5 allows to save money compared to R134A. So it looks like the most beneficial option considering the CapEx and OpEx and setup costs in all countries that have been studied. Here we have a map of Europe, and we can see that, of course, the operating and environmental costs have an influence depending on the salaries that are in some countries. For instance, in Germany, the operating costs will be higher than in other countries, while the environmental costs are more related at how the energy mix is produced. Poland depends a lot on fossil fuels, while, for instance, Sweden depends a lot on renewable energies. So basically, this is the map of Europe, but the most important thing is that we have a blend that can even result in a benefit, economically speaking, apart from the environmental savings. Just to conclude, I would like to say that I was expecting to enhance the role of thermodynamics in order to identify these effective fourth generation drop-in refrigerants. I just put a couple of examples using different KPIs and how, based on this thermodynamic information, we can take important decisions that can be used in the refrigeration industry in many different, but also in many different fields. As I said, it is also important to check the lubricant impact, and this can also be done using thermodynamics. And this work can also be extended, of course, to advanced cooling cycles and implementing other tools such as machine learning techniques that can be also useful to study other parameters that cannot be analyzed using an equation of state. I would just like to thank you, all of you, for your attention, and particularly I would like to thank you, Carlos Alba, because he has defended his thesis very recently, and most of these results are part of his work, and also long-term collaborators, Professor Lourdes Vega, Dr. Raphaelle González, Dr. Ismail Al-Hatib, and also the people from my research group. Thank you very much.
Yeah, thank you, Fèlix. Wonderful talk. I really enjoyed it a lot. And yeah, you have nicely shown the role of thermodynamics in optimizing not only the solvent but also the process as such, and the economics of what should be done best over the world, even locally, not only globally. Okay, so we collected already some questions from the board. The questions are what about not thinking in better solvent and improve the thermodynamics of the solvent? What about comparing this, what you have shown, with other technologies? Did you think about it, and are you on that, or will you do it in the future?
Yeah. I mean, of course, when we are talking about the different technologies, I mentioned that there are, I mean, here there are several aspects. From one side, there is the let's say cycle part, where we said that these studies have been applied not only to simple vapor compression refrigeration cycle, but also to other advanced cycles. I have not shown them due to, I mean, the time constraints. We have also done studies related to the other types of technologies like refrigeration by absorption, where this is completely different story, where instead of using a compressor, we use an absorber and a dissolver. And in terms of different, I mean, different technologies, we have also been using, let's say, other aspects of thermodynamics, such as, for instance, how we can recover these refrigerants at the end of life, how we can separate these compounds, how we can separate both of them, because as I mentioned, there were some that have a very high global warming potential, others have a low global warming potential. And we have used also thermodynamics to study possible solvents that can be useful in order to design a separation process of these solvents. So basically, the use of thermodynamics is not only related to evaluate the technical performance of the refrigerants, but also to study technologies to recover these refrigerants and reuse them, basically by absorption, membranes, adsorption, depending. Well, there is a very vast variety of techniques.
Yeah. Okay, thank you. A very brief question from my side about the fraction in the polar shaft, this XP. Does it need to be fit to a binary data?
No, the XP is fitted to the XP. First of all, there is an estimated value considering the molecule is seen. The amount of the scene is seen with also, first of all, chemically, and then with either with Cosmo or with another program, in order to see how the charge distribution is done. Then, based on the structure of the molecule, an XP value is proposed, considering, okay, we have 3 fluorine atoms, 1 hydrogen atom. It's located here. The polarity looks to be located in that area. So let's say more or less 70% of the molecule is affected by polarity. So at value of X equal to 0.70 is taken, and then the program is allowed to modify this value within some ranges. Let's say if at the end it's taken as a fitting parameter, but between a range of 0.6 and 0.8, you don't allow the XP to change a lot. Once this is done, the value of the mixture is taken with a mixing rule. You don't need binary data.
Okay, because that is what I know. That was the old way to fit this to VLE of binary mixtures or something like this. But very great. I think that is a big step forward. Then there is one question in the Q&A chat. Please take 1 minute after this discussion, Fèlix, to answer the first of these questions, because that is a question which concerns some detailed techniques, how you calculated exactly the environmental costs. So please answer that by yourself, and we will provide this answer afterwards also to everyone. Then a question from the industry, from Michael Kleiber. He wants to know about the global warming potential values of the alternative refrigerants that you have been suggestion. Are they so low because they decompose easier? And if they decompose easier, how about the global warming potential of these decomposition products?
Well, it's okay. The blends that we have proposed as a possible alternatives, and there is a patent on this regard. If I'm not wrong, I think that the global warming potential of blend number 5, I think it's around 30, so it's far below even 150. Okay. Because as I said, all the blends that have been proposed, they have passed a first step saying that the first condition in that path was to be below 150. Okay, so all the blends that have been studied are below 150 in the first selection. Okay, so second question is, how do we can estimate the global warming potential? Okay, the global warming potential is we normally take it from the IPCC reports. Okay, from the data, and I know that there are several techniques to estimate this, but we normally take this information in let's say we don't do any calculation respect to that. We take the values that are official, and we know that from one edition to another edition, sometimes depending on the way of calculation, they change. So we don't go into that. We just check that they are below 150. Finally, concerning the decomposition of the compounds, we honestly have not studied the composition of the compounds, so I cannot say for sure what is the global warming potential of these compounds in the decomposition stage. I know that there is always a problem with the atmospheric lifetime and the possibility of creating 3-fluoroacetic acid. As far as I know, the compounds studied are within similar ranges than previous ones, but this is a question that I cannot answer for sure. I should check it in order to be 100% sure.
Okay, then the last question from the audience. I had a little bit of the same question. Yeah, you have shown us the generation 1 to 4. What about the 5th generation? Do you have any feeling what this might be? And what my thought also to this was, can we survive without fluorine in these compounds?
Well, if I think that talking about fourth and fifth regeneration is something a little bit, well, it's kind of poetic, no? We like saying going from one generation to another. The truth is that there is a strong controversy about fluorine compounds. Indeed, there is a bunch of people who really think that even hydrofluoroolefins should not be used because there are also some flammability concerns, the composition, as it was mentioned before. And there is also a strong bet for hydrocarbons, okay? But hydrocarbons are also flammable and they also have many different issues, okay? So my feeling is that there will not be a perfect solution. There will be solutions that will depend on the type of air conditioner. I mean, it's not the same using a refrigerant for your fridge than using a refrigerant for the fridge of a supermarket, okay? So the use of hydrocarbons I think that will be implemented. Indeed, we are also studying mixtures of hydrocarbons, also CO2. I think that, okay, to make it short, I think that in short equipments where flammability and safety issues can be, how to say, taken care with, I mean, we have low amounts of refrigerant, hydrocarbons will play a lead. In high units, I think that fluorinated gases will still have will still be used, and probably the solution will go using not only binary mixtures, but multi-component mixtures.
I agree. So with this, I think I want to thank you, and I want to thank all the speakers in the name of the whole board. Thank you very much. Maybe just 1-2 sentences for the wrap up. Yeah, how to get a sustainable future. Yeah, that was the question we posed to this session, and I think we have seen 3 very different talks with the same goal. Yeah, applying thermodynamics and thermodynamics tools because it is our job and our duty to make the world more sustainable, right? This is what we can do, where we have the expertise and where we can help a lot. Yeah, and not only that, what also I like was not only seeing some chemicals like CO2 a bad guy, but also taking that as an opportunity to think of it like chemically, yeah, like a reactant again to make new chemicals and to make new products again. Yeah, we have once more seen that thermodynamics is all about efficiency. Yeah, whatever tool you can have, and we have seen a lot of tools, yeah, but finally we talk about efficiency, and that is what we can deal. That is what we can help. Yeah. And with this, I want to close my sentences and my talk. I want to give back to the head, to Grazia, and to the organizer, to Martin, and ask them if they want to add anything else.
Yes, just one last thing. Yeah, of course, thank you to all the speakers and to all the participants. I think it was a very, very interesting talk. I also want to remind you that we have an award open for submissions, the EFCE Excellence Award for Transport and Thermodynamics, for Transport Properties and Thermodynamics. It is awarded to the best PhD thesis published in the last 2 years, so 2023 or 2024. The deadline for submitting the nominations is the 15th of January 2025. There are some documents to present, so please, if you want to nominate someone, you have to be prepared and you have to do it with some advance. And if you need any further information, just let us know. Let me or someone else in the EFC organization know. And the prize is a cash prize and also the invitation to participate and present the work at the PPD conference, which will take place in May 2025 in Germany. So please consider nominating someone for this very important prize. So thanks again. And I hope I'll see you in the next edition of the EFC Spotlight Talks in spring 2025. Thanks. Bye, everyone.
Thanks all.
Thank you.
Bye-bye.
Bye-bye. Thank you.